Hey guys, today we're going to be talking about solutions. The first time you heard about solutions should have been way back in Unit 2 when we learned that a solution is a homogeneous or homogeneous mixture. What that means is that you can't see the different components of the mixture. So everything is going to look the same. And that's going to happen with solutions because solutions have one part of the mixture dissolved into the other part of the mixture. For example, salt water has salt and water mixed together, but the salt is dissolved into the water, so you can't see them separately anymore. The same thing happens with sugar water. That's kind of a cop-out example because it's just about the same. But also this happens with tea, lots of other drinks. It does happen with plenty of chemicals, but a lot of those are not super well known to you. Another one that you might know of, or a couple of more, are like hydrogen peroxide is a solution of hydrogen peroxide in water. The stuff you buy at the store is a solution. Same with isopropyl alcohol or rubbing alcohol. Those are solutions of chemicals dissolved in water, and you actually can't even hardly tell there's a mixture there because you can't see the different components. So if you didn't know beforehand, you might not know that was a mixture. Now, every solution has two parts, the solute and the solvent. The solute is it's the chemical or the compound that is dissolved. And then the solvent is what it dissolves into. Got to get that all written down there. So, for example, if we look at the salt water, in here, if this is water, we're going to have tiny little grains of salt. You won't be able to see them because they will be dissolved, and we'll see what that actually looks like on an ionic level here in a minute. So in this example with salt water, the solute, the chemical that is dissolved, or the thing that's dissolved, that is salt. And the solvent, the thing that is dissolving into, is the water. One of the kind of mental tricks for remembering these two is the V from solvent can open up and hold inside it the solute. So the solute goes into the solvent. And then we call water the universal solvent because it can dissolve so many different things. And we'll actually see here in a second why that is. So water is a polar molecule. You learned about that way back in, what unit was that? Unit 3. When we were talking about compounds, we did the Vesper chart with molecule shapes. We learned that water is a bent molecule, which happens to be polar. And when a molecule is polar, that means its charge is not evenly distributed. So it's going to have a more positive side and a more negative side. So we're going to draw a picture of that here. This is going to be my water molecule. One hydrogen with two little oxygens. I'm not labeling them, but the hydrogen's the big one. The oxygen's the big one in the middle. Hydrogens are the two small ones on the side. And there is a larger distribution of negative on the side with the oxygen, which is pushing away those other bonds to give a positive side of the water molecule over there. So it's got a positive and negative. And if you know anything about electric charges, it's that positives and negatives attract, and then positives and positives repel, negatives and negatives repel. So when you put a bunch of water around a compound, say sodium chloride, you've got sodium that is naturally a positive ion combined with chlorine, which is naturally a negative ion. So what happens is that our sodium here is attracted to the negative end of the water because the sodium is naturally a positive ion. And then the chlorine is going to be attracted to the positive side of a water molecule. So they'll end up being pulled to the water molecules, which will cause them to spread apart a little bit. And when they spread apart a little bit, That's called dissociation. So water, because it's polar and has a positive and a negative end, is really good at dissolving things because it can pull on those ions and split them apart, which causes dissociation and makes a substance dissolve. Now, when a compound splits into its ions, those ions are called electrolytes. And the reason we call them electrolytes are because they can conduct electricity, which is really cool. You can ask your teacher, well, if you're watching this video, you can't ask your teacher, but you can look in your Google Classroom, and I'm sure there will be a video attached showing a demonstration that we're doing in class where you can take a light bulb and put it into a solution, and based on the amount of electrolytes it has, it will either conduct electricity really well or not at all, but it can, in fact, if it's a strong electrolyte, conduct a lot of electricity. So the deal with strong electrolytes is that they are compounds which dissociate completely. So an example of a strong electrolyte is like hydrochloric acid, HCl. It can dissociate completely, which means in a solution, so here's going to be my crappily drawn beaker, every single molecule will dissociate into its ions. So every single HCl will split apart to be H plus and Cl minus. So all of those molecules will split. 100% dissociation, which means there's lots of positives and negatives for electricity to flow through, and it will light up a light bulb really, really bright. Now with weak electrolytes, they only dissociate partially. They still form electrolytes, which are those ions conducting electricity, but only partially. I believe hydrofluoric acid is an example of this one. So you would end up with some H's separated from their F's, but also some that are still together. So because some stay together, it can't conduct electricity as well because some of them are still together, not in ion form, so they don't completely dissociate, but they do somewhat, so they can still conduct electricity, but not as well. So our first one, the strong electrolyte, will have a very bright light bulb. The weak electrolyte would have a dim bulb, and then a non-electrolyte is one that does not dissociate at all. So that one does not dissociate. An example of this is sugar. Either sucrose or glucose. I'm doing glucose, C6H12O6. Those molecules will stay together in their entirety, but the water is able to separate each individual molecule, not from its other parts, but from the other molecules, until they get so small that you can't see them anymore. So it's still called dissolving, but it's not splitting it into its ions. And because it doesn't split into ions, the non-electrolyte will not conduct electricity at all. So the answer to this question, which one lights up the bulb the most, is our strong electrolyte, because it forms the most ions. Now, another thing we need to discuss with solutions and solubility is rates of solubility. So solvents can only dissolve solute so well. It can only hold so much solute, and the rate at which it can dissolve the solute is dependent on several things. So if you've ever tried to stir sugar into like cold sweet tea, you'll know that it doesn't dissolve super well. But there are certain things we can do to increase the solubility of a solid like sugar into a liquid like sweet tea. So one of the ways to do this is to increase solute to solvent interactions. And a good way to increase solute to solvent interactions is by stirring. So anytime you're trying to dissolve something, you're stirring it around to try and get those solute particles close to the solvent by stirring, so it increases their interactions. Another thing you can do is crush up your solute. So you say crushing, grinding also works, and that increases the available surface area. So every grain of your solute, like of salt or sugar, is or has a certain surface area with a certain number of molecules, because molecules are obviously much smaller than a grain. So if you crush those up, you're exposing a lot more molecules, so it's able to interact with your solvent better. So crushing increases the surface area, which really helps it be able to dissolve faster. And then another way that you can increase solute to solvent interactions is with heating. So if you've ever made sweet tea on your own at home with like a tea bag, you would know that it's best to stir in the sugar while it's still hot. And that's because, as we discussed with our gas laws, temperature is based on the kinetic energy of particles. So if the particles are moving a lot faster, the solute and the solvent interact more because they're getting around better. So those interactions are increased, meaning it can dissolve a lot faster. So for the example here, you can put sweet tea is a good example. Now, you might not think too much about dissolving a gas in liquid because that just seems a little bit foreign, but actually you see this all the time. The example we're going to be using here is a soda, or like we enjoy calling it in East Texas, a Coke. So when you dissolve a gas in liquid, it tends to want to come out, which is what happens with a carbonation in your soda. And there are 3 ways that you can help keep that gas dissolved in the liquid. And we're very familiar with this for sodas. One thing you can do is keep it in the fridge or keep it cold. If you keep your sodas in the cold in the fridge, then they are less likely to go flat. Another thing you can do is keep it still. Keeping your soda still instead of shaking it helps keep that carbonation dissolved in your soda. When you shake it up, it releases that carbonation, and you end up with usually a mess on your hands. And the very last one is that you can keep it closed. Keeping it closed keeps a certain amount of pressure on it, and when there is pressure, your gas is less likely to escape your liquid because it likes to be in areas of lower pressure. So when you keep that pressure outside high, it helps keep the gas from escaping. So to keep your soda nice and carbonated, to keep that gas dissolved in liquid, you keep it cold, you keep it still, and you keep it closed. All right, next up in our discussion of solutions is the idea of saturation. So we've already talked about solubility rates and seeing how much solute a solvent can hold, and that idea is the basis for saturation. So the idea here is that a solvent can only hold so much solute before it becomes saturated or full. Sorry, that doesn't look like the word saturated, but it is the word saturated. There are 3 levels of saturation. So an unsaturated solution means it is not yet full, or it can hold more solute. And this is always specific for a given temperature. So you're talking about at a given temperature. If you increase the temperature of a liquid, it becomes more salt or can hold more solute. And if you decrease the temperature, it can't hold as much solute. So this is for a specific temperature. So if it's unsaturated, it's not full. It can hold more solute. If it's saturated, it is exactly full. It has just the right amount of solute, exactly full. And then super saturated is it has too much solute or is too full. So what's going to happen when you have a super saturated solution is that your solute starts to come out of your solution, starts to fall out or precipitate in your solution. So you end up with things like rock candy, which is a super saturated solution of sugar. And as it cools down, because it can hold a lot of solute when it's hot, but as it cools, it becomes super saturated and it starts to get rid of the sugar. The sugar falls out of the solution and it forms those nice crystals for rock candy. And that happens with super saturated solutions. So you've got unsaturated, can hold more solute. Saturated has the exact right amount of solute. It can't hold any more, but none's falling out. And then supersaturated means there's too much. That solute is going to start coming out of the solution. Okay, our next topic, approaching the last, is polarity. And we've already talked about this with water a little bit. But there are both polar and nonpolar molecules that exist in nature. And the rule for dissolving things is that like dissolves like. And what I mean there is that a polar solvent can only dissolve polar solutes. Polar dissolves polar. And then the opposite is also true. Nonpolar solvents can only dissolve nonpolar solutes. So if you've got something that's polar mixing with something that's nonpolar, they will not mix well, they will not dissolve. This is what happens with oil and water. Oil is nonpolar, water is polar, so they cannot mutually dissolve because they are not alike. They have to be alike in order to dissolve. So what happens in that situation is that the water molecules actually stick together due to their property of cohesion. And when they stick together, they push the oil molecules out. So you end up with oil and water separating, which I'm sure you've seen in your life at some point. I at least see this a lot with cooking. When you cook and you have both water and oil in the same space, you get little pockets of oil or pockets of water, but they do not mix well in the same area. One way that we can get these two to work together is with soaps and detergents. So I'm sure you've all had an oil stain or some sort of oil get on your shirt and you need to get it out. And water just doesn't do the trick because oil is non-polar and water is polar, and those two don't work well together. That's where soaps and detergents come in. They are chains that have a polar end and a non-polar end. So they're able to work with both polar and non-polar molecules. So what happens is that your soap, which we kind of just draw as a weird squiggly line, that's not really correct, but just go with it. One end has a positive and negative, and the other one is neutral. So this end is polar. This one is non-polar. The polar end can attach to the water molecules, which look like this. The nonpolar end can attach to the oil. I'm just labeling it as oil. So that soap can bind the water to the oil, which means you can use your soap or detergent to stick to the oil stain in your shirt, and then the water to stick to the other end of the soap, which pulls the oil out. So you end up with a nice, clean, unstained shirt. So soaps and detergents are really, really cool chemicals that somehow are able to interact with polar and non-polar materials, which is really cool, really useful. It's how you get grease out of everything. All right, well, that's all I have for you today about solutions. We're going to be moving into acids and bases, which are typically found in solution, next week. So stay caught up. You do have a practice in Google Classroom where you're going to be drawing some of these solutions. So go take a look at that. Let us know if you got any questions.